Last video was all about the Jacobian. Remember, this is our definition here of the Jacobian. So one little discussion I want to have is how area changes with Jacobians. Suppose we have domain D and a map G, the coordinate transformation here. If G is linear, then the area of G of D is exactly equal to the absolute value of the Jacobian of G times the area of D. So the Jacobian tells you how much you scale, what the factor is that you scale the area of your region by. So if this region here is, area is equal to 4, and the Jacobian here is 7, then this area will be 28. Now, even if G is not linear, we can say that the area of G of D is now just approximately equal to the absolute value of the Jacobian D times Jacobian G times the area of the original thing. We have to pick a particular point in the region to evaluate the Jacobian at. This gives us some approximation, and of course, as we, and in the limit, we take things be smaller, 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 this becomes a better and better approximation. So Jacobians tell you roughly how much you're scaling the area of the region by. And so all of this brings us to our big theorem here for this section, Theorem 3, substitution for double integrals. Suppose that our function f of xy is continuous over a region R. Let G be the pre-image of R under the transformation x is equal to g of uv, y is equal to h of uv. This is going to be 1-to-1 on the interior of G. If G and H have continuous first partial derivatives within the interior G, here is our formula. The double integral over R of f of xy dx dy is equal to the double integral over G of f of g of uv, h of uv, times the absolute value of the Jacobian, du dv. Okay, so what's going on here? First off, this absolute value of the Jacobian, that's exactly, this factor right here. It's telling you how much you're scaling the area by. So that is good. Also, the thing that we should be thinking about here is that this region R is probably going to be a nasty region. This region G needs to be a nice region. The idea is that instead of integrating, the idea here is that you are given a double integral over a nasty region, a region you don't really want to integrate over. And so what you do is that you apply the change of variables, you replace x with a function of uv, y with a function of uv. You make that replacement here, and you're integrating over the nice region, and the thing is that you have to throw in this factor of the absolute value of the Jacobian. And so now we should really see all of these things tied together, because the Jacobian for this transformation here, the polar coordinates transformation, is R. This explains why we throw in the factor of R when we convert to polar coordinates. So it should all be kind of coming together at this point. Let me also, on the following slide here, let me kind of emphasize the substitution aspect. Sometimes I call this change of variables. We're changing x and y to u and v. This textbook really emphasizes substitution. So let me emphasize the substitution here. This line is just the bottom line of the previous line recopied here. This line down here is substitution in one variable definite integrals. The integral from g of a to g of b of f of x dx is equal to the integral from a to b of f of g of u times g prime of u du. So realize what's going on here. This g prime of u, that's the derivative of our transformation, or derivative of our map here. That factor gets thrown in just like the absolute value of the Jacobian gets thrown in here as well. And this makes sense. The Jacobian with its partial derivatives, this is our best attempt to define what the, quote unquote, the derivative, this is what the derivative of this transformation is, in the sense that it's playing the same role as g prime of u is here in one variable substitution. And so, we can go back and forth between these. We can go back and forth between these. Okay, so this is our main theorem for the section, the nasty and the nice. We're given this integral over the nasty region. We use a change of variables to figure out what the nice region it came from is. And so this is where we are going. So the idea, let me just, compare nasty and nice here. The idea is something like this. We have a weird looking region in the XY plane, but we can say in the UV plane, we can come up with a mapping here. The x is equal to little g of uv, y is equal to little h of uv. We can come up with a mapping that sends this nice g to this nasty r here. And then if we can do this, instead of integrating over the nasty r, we integrate this over the nice g. It makes our life a lot easier. And I have a bunch of examples queued up ready to go.